Hi everyone, welcome back. This is not actually a lecture for MATA35. This is the review session, which I'm calling, in quotes, Lecture 13. We're just going to be going through the material that that you should know for the final exam. So obviously I'm not going to be able to cover everything in a 12-week-long class in a 1-hour review session, but I'm going to cover many of the highlights in brief detail, just so that I can remind you what you really need to know for the final exam. Let's go ahead and get started. I will be going quickly, so normally I try to slow down and ask questions for participation. I will be doing none of that today. If you really have questions, please just ask in the chat, and I will be watching out for that. So this will be a much more traditional lecture. I'm just going to throw a fire hose of information at you. So, first things first, you should know all the basic integral, derivative and integral tables. These should all be old hat by now. You will need to know everything up through derivatives of sines and cosines. Hopefully there aren't any questions about that. The other thing, you will need to know the basic derivative rules. So for example, things like the chain rule. So if you have a function, let's call this f of x is equal to x squared. We have f prime of x is equal to 2x, and g of x, let's say 3x minus 1, and g prime of x would be equal to 3. Then d dx, the derivative of 3x minus 1 squared, is going to be equal to 2 times 3x minus 1 times 3. Yes, we had a question. Yes, you need to know everything on here. This is very important. These are things that I just assume in the background, and I almost forgot to put this on here. So know all of this. You will need to know the chain rule. You will need to know the product rule. So if you have these two functions, f of x and g of x, so then d dx of x squared times 3x minus 1 is equal to x squared times 3 plus 2x times 3x minus 1. And lastly, you should also know the quotient rule. So this is d dx of, let's say, x squared divided by 3x minus 1. That's going to be equal to the, it's all going to be over the bottom squared. It's going to be the bottom times the derivative of the top, 3x minus 1 times 2x, minus the top times the derivative of the bottom, times 3. Okay, so review of basic derivative techniques from back from A29. You will need to know a bunch of integration techniques. So in addition to knowing the integral table, you will need to know the substitution method, which involves guessing an appropriate u, computing du, dx, and dx, substituting to get rid of the x's, integrating as a function of u, and converting back to x's. So let's give a simple example of that. If I gave you the integral of 2x e to the x squared dx, well, if we let u be equal to x squared, du is equal to 2x dx. We substitute all of that in. This is equal to the integral of e to the u du. This is equal to e to the u, which is equal to e to the x squared. You will need to know integration by parts. So you should memorize this formula. Integral of u dv is equal to uv minus the integral of v du. There is a heuristic we gave, which is in your notes. This detail heuristic where you try to guess which one is which. You apply the formula to see if it works. And hopefully it does. If it doesn't, you might need to do a different guess. So, just a moment. So let's give a quick example of this. If I gave you the integral of x e to the 2x dx, well, u here, we're going to guess that's equal to x because it's algebraic. And we're going to guess dv to be equal to e to the 2x dx. And v is equal to 1/2 e to the 2x. And du is equal to dx. We plug everything in, and you end up getting that this is 1/2 x e to the 2x minus the integral of 1/2 e to the 2x dx, which is equal to 1/2 x e to the 2x minus 1/4 e to the 2x plus c. Okay, and lastly, this isn't really an integral technique, but we covered it in the integral technique section, where we have partial fractions. So remember, if you're adding together two fractions, a over ax plus b times cx plus d, well, when you add them together, you just multiply, you combine the denominators and numerators, and you end up with a times cx plus d plus b times ax plus b. Now, this also means that if you start with the right-hand side of that equation, you can figure out what a and b should have been. So, if you started with, let me do a simple one, 1 over x squared minus 1, that's equal to 1 over x plus 1, x minus 1, which we know is equal to something, a over x plus 1, plus something else, b over x minus 1. Okay, I'll slow down a little bit. So I'm probably talking really quickly. I have a tendency of talking at a mile a minute. Yes, okay. So we assume that there is something we can do with a and b such that this equality holds. So we need to solve for that. So we need to solve for a times x minus 1 plus b times x plus 1 is equal to 1. You combine to get all the terms, you get a plus b times x plus b minus a times 1 is equal to 1. And so you have a plus b is equal to 0, and minus a plus b is equal to 1. Combine these together, you get a is equal to minus 1/2, and b is equal to 1/2. You plug those in, and then you can turn this 1 over x squared minus 1 into these two other fractions, which is sometimes easier to take an integral of because those are all just logarithms if you take the integral. Okay, so this is the review of week 1 and 2. You need to know basic integration and their derivatives, and be able to use all these different rules. These things, there will be problems on the exam that can be solved using these sorts of techniques. Notably, on some of the differential equations, on the problems, I forget which ones, what number they were, but on some of the problems you will be doing some ODE solving. Some of them will involve integrals, and there will at least be one of them that involves that can be solved using integration by parts. There will be one of them that can be solved using partial fractions. You don't necessarily have to use those techniques all the time, but often those will be the easiest ways of doing it. So that is just for the ODEs. Not necessarily. It could be anywhere in the exam, but like most of the times, the more complicated techniques will probably be in some of the ODEs. Because let's see, yeah. Though the entire exam is pretty integrated, so you shouldn't assume that you only need one technique if you're in one place. Okay, next, matrix multiplication. So we have a matrix multiplication formula. It's really complicated when you write it out. It's less complicated to actually see. Basically, you take if you had 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's say we're multiplying this by 2, 1, 3. So the way it works is you take each of the rows of the first matrix and multiply it by each of the columns of the second matrix. In this case, there's only one column, and so this is equal to 1 times 2 plus 2 times 1 plus 3 times 3, and 4 times 2 plus 5 times 1 plus 6 times 3, 7 times 2 plus 8 times 1 plus 9 times 3, which I think, if I wrote this down correctly, is equal to 13, 31, 49. And of course, if you have multiple columns, you'd have multiple columns in your final answer, and you'd do the same thing. So basic matrix multiplication. We also learned how to compute eigenvalues and eigenvectors. This is true for any square matrix. If you have a square matrix A, an eigenpair lambda v is any pair such that AV is equal to lambda v. So where multiplying by the matrix is equivalent to multiplying it by this lambda. You can compute the eigenvalues by taking the determinant, lambda I minus a is equal to 0, or a minus lambda I, it's equivalent. And then you can compute the eigenvectors by solving. So let's solve one of these quickly. We've done a lot of these, so I'm not going to spend too long on this. So if you have 7, 8, minus 4, minus 5, which I think is one of the matrices I put in the practice exam, then you solve this by taking lambda minus 7, minus 8, 4, lambda plus 5. Take the determinant of that. That's equal to lambda squared minus 2 lambda minus 35 plus 32 is equal to 0. Lambda squared minus 2 lambda minus 3 is equal to 0. Factor that out. Lambda minus 3 and lambda plus 1 is equal to 0. So lambda is equal to minus 1 or 3. So once you've computed the eigenvalues, you can compute the eigenvectors. Let's just do it for lambda 1 is equal to minus 1. There's obviously an eigenvector also for lambda 2 is equal to 3. So you multiply. You just use this equation now. So 7, 8, minus 4, and minus 5 times some vector xy. And we need to solve for xy is equal to minus 1 times xy. So minus x minus y. When we solve these, for the 2 by 2 matrices, it's actually easier because if you have an eigenvector like this, oftentimes you only need to get rid of one. You only need to look at one of the equations because the two equations will be linearly dependent. So you have 7x plus 8y is equal to minus x. And that implies that 8y is equal to minus 8x, and y is equal to minus x. So v1 is equal to 1 and minus 1. And of course, you can do the same thing for lambda is equal to 3. And it gives you eigenvectors. So that's basic matrix operations, multiplication, as well as eigendecomposition. Well, an eigendecomposition requires you to get multiple eigenvectors. So, for the biological application, we have Leslie matrices and diagrams. Question: for diagonal and triangular matrices, the eigenvalues are on the diagonal. Yes. So it turns out that if you apply that formula when you have a diagonal matrix, the determinant of lambda minus the diagonal matrix is just lambda minus each of the terms on the diagonal, and when you solve that, lambda is equal just to the diagonal entries. Yeah, so that's a very important special case. Okay, so what are Leslie matrices? So this is Leslie's age-structured biological population model. In the Leslie diagram, each arrow represents how each life stage gives rise to individuals in the next life stage. For example, if you had a 3-life stage model with hatchlings, juveniles, and adults, the arrow from hatchlings to juveniles means that from the hatchling stage to the juvenile stage, 0.5 of them survive, or as a result of there being one hatchling this year, there are 0.5 juveniles next year. Or if as a result of there being one juvenile this year, there are, let's say, 0.9 adults the next year. And the arrow from adults often goes down to hatchlings, depends on the model, but an arrow from adults means as a result of there being one adult this year, there are 5 juveniles next year. And we can encode all this into a matrix. Each column encodes all arrows that start from the corresponding node. Each row encodes all arrows that end in the corresponding node. So of course, for matrix, you have to order things. Usually we order things in the same order that we order the life stages. So let's say hatchlings, juveniles, and adults. Hatchlings, juveniles, and adults. How many hatchlings are there as a result of there being a hatchling this year? Well, 0, because there's no arrow from H to itself. But there is an arrow from H to J, and so you get row 0.5. There's no arrow from H to A, so that's 0 again. For juveniles, I didn't give a number for that. Let's say 5. For juveniles to adults, there's a 0.9, but there aren't juveniles to anything else, so those are 0. For adults, you get 5, 0, 0. So in this particular model, the adults all die out after an iteration. So often these will be years or months, but there will be whatever the generation time is. Or not generation time, but whatever the iteration cycle time is. And one of the nice things about Leslie matrices is that you can predict the population after a year or two. So, if you're given a Leslie matrix L and a current population vector P, so how many current hatchlings, juveniles, and adults there are, the population one cycle later, however long a cycle is, will be the matrix times the vector, LP. 2 cycles later will be L times LP, which is equal to L squared P, etc. Furthermore, the population one cycle earlier can be computed by solving the equation Lx is equal to P, or by using the matrix inverse and computing x is equal to L inverse P. Depends on what exactly you're doing. So if you're doing multiple cycles back, it might be easier for you to just compute the matrix inverse once and multiply. If you're doing only one cycle back, it might be easier to just solve the equation Lx is equal to P. And you can solve the equation using things like Gaussian elimination or just using various other methods for solving a system of equations. Okay, so that is Leslie matrices. So that covers, roughly speaking, problem 1 on the final exam. Will it be relatively simple, or do we need to know the 1 to 2 generations, or do we need to know the eigenbasis method? It will be the problem that you will be seeing on the final exam will be very similar to the practice exam problem. So I'll leave it at that. Okay, so separation of variables. So now we're going to look at the techniques for solving ordinary differential equations. This is in particular a way of solving a first order ordinary differential equation. So if we let dy dx be equal to some function of x times some function of y that are separable, which means that you can divide out and get all the y's on one side and all the x's on the other side, then you can just integrate both sides. So if I give a very simple version of this, this might be y prime is equal to 2x plus xy. And let's say dx dy is equal to x times 2 plus y. And then we have dy divided by 2 plus y is equal to x times dx. We can integrate both sides of this, and you're left with natural log of absolute value of y plus 2 is equal to 1/2 x squared plus c. Y plus 2 is going to be equal to c e to the 0.5 x squared. Y is going to be equal to minus 2 plus c e to the 0.5 x squared. Okay, so there are a couple important things that I should mention here. The first is note that you're doing a couple of integrals. Those integrals on the final exam could involve any of the integration techniques we're talking about, including things like integration by parts on the exam. The other thing is, on the exam, you'll also often have an initial value problem. So if you have an initial value problem, you might have something like y of 0 is equal to, I don't know, 3, in which case that would imply that c is equal to 5. And so y is c times e squared. Ah, yes. So this was one of the things we, so this is actually equal to this plus c, right? But whenever you multiply that out, you can change this. So you can change this to, instead of just being plus c, that's also equal to that times e to the c. But e to the c is just some other constant. And so you can replace that with some other constant, c. Yeah, so you do have to be careful. And could we keep it as plus c? You could, but it'll make your life harder. So if it's an initial value problem, do you answer as an equation or a value? You answer as an equation. So once you get that, then let me actually write this up a little bit. So let me, actually I have lots of space here because I don't have a poll going. So if you had an initial value problem version of it, let's say that y of 0 is equal to 5, is equal to 3. Then you plug that in, you get 3 is equal to minus 2 plus c e to the 0. And so then you get that 5 is equal to c. So c is equal to 5. And so the equation is actually y is equal to minus 2 plus 5 e to the 0.5 x squared. Yes, initial value problems just mean that you need to calculate c. Sometimes you'll have multiple c's, in which case you need to calculate multiple. So sometimes you have c1 and c2, in which case I'll give you 2 initial conditions, and you need to solve a system of equations to calculate both c1 and c2. So this will happen if you have a higher order equation or if you have a system of equations. Okay. So that's one type of problem. We also have exact differentials. Which are very similar to separation of variables in some ways. So in many of these cases, I'll go ahead and give you an exact differential in this form where I've separated out something times dx and something times dy. You unfortunately won't be able to separate out into 2 completely different integrals, and so you have to integrate it all together. A question. Can you explain the plus c part again really quickly? Which plus c part? So we have this plus c here because that's an integral, of course. And note that, okay, let me just write over to the slide. So when we take the e to the c, we get e to the c, right? So if you have e to the c times e to the 0.5 x squared, well, you let some c2 be equal to e to the c. And then you have c2 e to the 0.5 x squared. It's just some other constant. And because it's just some other constant, sometimes you can play fast and loose with the constants. Basically, when nothing else depends on the constant, you can play fast and loose and just replace it with some other constant. If you are uncertain with how to do this, just explicitly write down the fact that it's some c2 is equal to e to the c. Okay, but anyway, so when we're talking about exact differentials, basically, if there exists some function f of xy such that the partial derivative of f with respect to x is equal to p, and the partial derivative of f with respect to y is equal to q, then you can solve it as just f of xy is equal to c. it is often quick to check whether or not it's an exact differential by just taking the partial derivative of p with respect to y and checking if that's equal to the partial derivative of q with respect to x. So let's go ahead and give an example. It's not the one I did earlier, but it's a slightly simpler one. Will the equation on the exam be exact, or do we have to check? It will be exact. It will be exact on the exam. In general, you do always have to check. But that's not quite true. So the real answer is that if you do the integral part of it properly, if it's not exact, it just won't work out. And so you don't necessarily have to check. But usually doing the integral is more time consuming than just taking a derivative. And so often in practice, you'll check using this alternate technique and then decide whether or not you need to do the integral. You didn't check on the... So on the quiz, I think I did require you to check. But I will tell you on the exam, you will not be required to. So yes, I will not be making you use an integrating factor. Or if I do, I will give you an integrating factor, which I'm not, because that's just not on the exam. And I already wrote the exam. So yeah. So what practice problem does exact differentials fall under? It falls under, which one is that? Sorry, let me pull it up again. On the practice exam, the exact differentials is 4.3. Okay, but anyway, let me continue on with this. So integral of 2e to the x squared plus y dx plus, let's say, x dy is equal to 0. So let's go ahead and check, because that's good practice. So then d dy 2x e to the x squared plus y is going to be equal to 1. d del x of x is also equal to 1. And so this is exact. Now we need to take the integrals. And so we have integral of 2e to the... Oh, sorry, let me put an x there. It'll make life easier. So 2x e to the x squared plus y dx. What is this equal to? Well, y is constant as far as this is concerned. And so this is equal to e to the x squared plus xy plus some constant. But the constant can be a function of y. The integral of x dy is just equal to xy. And the constant can be some function of x. So then you match together the terms. So here we have this x e to the x squared, which is some function of x. We have this xy, and we don't have anything here, so maybe this is just plus 0. So in our or some plus some constant. It doesn't really matter. So then when we match these things together, that implies that e to the x squared plus xy plus c is equal to 0, or is equal to c. It doesn't really matter, because you can move the c on either side. Can you use c as your constant? So you have to be really careful here, because is that y or x squared? Which one? Power v. Oh, well, that's e. Those should all be x's. Yeah. Is that a little bit more clear? Yeah. So you have to be a little bit more careful, because here, when you integrate and get a constant, the constant can't, because as far as the first integral is concerned, y is a constant. So your constant can be a function of y. And in the second integral, your function can be a constant, can be a function of x. Actually, let me rewrite this. That should be a g. So let's say call that g of x. And so if you write it as a constant, you may forget that it can be a function of the other variable, which is why I don't recommend it. If you can keep track of that in your head, you can write it down that way, but I think that that is a very easy way of making a mistake later. Why is the integral of 2x e to the x squared e to the x squared? Because that was the substitution method that we solved back here. So Remember how I told you at the very beginning of class that all these integral techniques, you'll have to like know like the back of your hand? Well, they show up everywhere. So there might be random ones here where I just expect you to recognize immediately that that's a U substitution. Okay, where was I? Exact differentials. So you're left with this function, and if there were an IVP, then you would need to solve for C as well. So you should assume that there might always be an IVP. For the exact differentials, you will be allowed to leave it in implicit form. So here, in this one, you could actually rewrite it as y is equal to exactly something, but oftentimes for these exact differentials, when you're integrating it, writing it in the explicit form y is equal to something is a little bit hard. So I will allow you to leave these in implicit form. Okay, now we're getting into the more recent material, constant coefficient homogeneous equations. So for these, you just need to find all roots of the characteristic polynomial. A root with multiplicity 1 means that e to the lambda x is a solution. A root with multiplicity k means that x to the k minus 1 e to the lambda x is a solution. You take all linear combinations of these solutions. So, for example, and you also have to be careful about complex roots because then you might have sines and cosines, which I think I forgot to write down. But for example, y double prime plus 4y prime plus 4y is equal to 0. Then you have a characteristic equation. Lambda squared plus 4 lambda plus 4 is equal to 0. Lambda plus 2 squared is equal to 0. Lambda is equal to minus 2, multiplicity 2. And so you end up getting y is equal to c1 e to the minus 2x plus c2 x e to the minus 2x. Similarly, there is a special condition for complex roots. So if you had something like y double prime plus 2y prime, say, plus 2, that should work, plus 2y is equal to 0, then you get a characteristic equation, lambda squared plus 2 lambda plus 2 is equal to 0. And this is equal to, well, lambda plus 1 squared is equal to minus 1. Lambda plus 1 is equal to plus or minus I. Lambda is equal to minus 1 plus or minus I. And so then y is going to be equal to c1 e to the minus x cosine x plus c2 e to the minus x sine x. Okay, so remember that you also need to know how to do it for complex roots. Okay, so that is the constant coefficient homogeneous. We did a lot of practice on that one in class. The other thing you need to do is sometimes you have an inhomogeneous equation. So there we have to use the method of undetermined coefficients. So the first thing you do is you find your homogeneous solution. So let's go ahead and do the one from before, y double prime plus 4y prime plus 4y. Let's say it's equal to x. Well then your homogeneous solution is just the solution we had earlier. So let's c1 e to the minus 2x plus c2 x e to the minus 2x. And then you have to guess an ansatz for the particular solution that has terms corresponding to each of the derivatives of the terms on the right-hand side. So here, your particular solution ansatz would be yp is equal to ax plus b, because you also have to correspond to the derivatives of x, which are just 1 and 0, but you don't care about 0. You solve this, yp prime is going to be equal to a, yp double prime is going to be equal to 0. You plug that in, so yp double prime plus 4yp prime plus 4yp is going to be equal to, you plug all those things in, so you have 4yp prime, so that's 4a plus 4yp plus 4 times ax plus b. So that's equal to 4a plus 4ax plus 4b is equal to x. You solve this, you get 4a is equal to, I got this right. 4a is equal to 1, and 4a plus 4b is equal to 0. So a is equal to 1/4, and b is equal to minus 1/4. And so that leaves you with yp is equal to 1/4 x minus 1/4. And the next thing to do is you get your general solution by combining the homogeneous and particular solutions. And so then y general is going to equal c1 e to the minus 2x plus c2 x e to the minus 2x plus 1/4 x minus 1/4. And note that you will often have, and you may have an initial value problem for this equation as well. If I give you an initial value problem with this equation, then you need to solve for both C1 and C2. So I'll give you two different initial conditions, maybe y of 0 and y prime of 0, or something like that, and then you need to solve for both C1 and C2. Okay, so that's the method of undetermined coefficients for an inhomogeneous constant coefficient linear ODE. And now we're going to talk about homogeneous linear systems. So there are two ways of solving this. I'm just going to review the eigenbasis way of solving it, since if it's homogeneous, the eigenbasis method is often easier, though it doesn't always work. I can just go ahead and tell you, like, the eigenbasis method will also work for the problem that's on the final. You can always use the substitution method, but the eigenbasis method will work. So if we start out with some equation, x dot is equal to 7x plus 8y, y dot is equal to minus 4x minus 5y. We can rewrite this as a matrix equation. Xy is equal to 7, 8 minus 4 minus 5 times xy. This only works for constant coefficient homogeneous linear ODEs. There are ways of extending it to other types of matrix equations. We did not cover them in this class, so I'm not going to expect you to know them. There are ways of doing it, and if you were to take a B44, if you took B44, we would cover these other ways of using these as well. But this is A35, not B44. Yes, the eigenbasis method is the matrix method. Yeah. And so there are many times when this does work, and when it does work, it tends to be easier. So what you do is you need to do an eigen decomposition. I'm not going to redo it. So lambda 1 is equal to minus 1, v1 is equal to 1 minus 1 from previously when we did partial eigen decomposition. You can do the same thing for lambda 2. That's going to give you lambda 2 is equal to 3, v2 is equal to minus 2, 1. And together this implies that xy is equal to c1 e to the minus t times 1 minus 1 plus c2 e to the 3t times minus 2, 1. And you should expect to be able to solve an initial value problem with these as well, to solve for c1 and c2. So all these problems where you end up with c's, can you do an initial value problem for this? Yeah, sure. Let me do that. So let's suppose that I said that x of 0 was equal to minus 1 and y of 0 was equal to 0, let's say. Okay, so if I gave you these initial values, what you'd do is you'd plug these things in. So then you'd be left with, let me say this would be minus 1, 0 is equal to c1. Since I gave you, since e to the 0 is always equal to 1, so c1 times 1 minus 1 plus c2 times minus 2, 1. Then we just need to plug it all in. So minus 1 is equal to c1 minus 2c2, and 0 is equal to minus c1 plus c2. I'm going to add these together, and so that gives me minus 1 is equal to minus c2. So c2 is equal to 1. Plug that back in. You get c1. Oh, that's behind me. Let me get rid of myself for a moment. So you get c1 is also equal to 1. And so therefore your final solution is xy is equal to e to the minus t 1 minus 1 plus e to the 3t minus 2, 1. Could you solve this question using the substitution method? Yes, you can also solve it using the substitution method. Could you do an example using a harder IVP, since y0 is equal to 0 was like a nice number? Okay, sure. Let me do a slightly harder one. Give me a moment. I am going to go ahead and erase this since I'm out of space, and I'm going to redo this with a harder number. So, okay, so let's say that x of 0 is equal to 4, and this is equal to minus 3. Okay, so again, we would plug everything in. Let me switch to using blue on this. So if we had this initial value problem, so this is an IVP, then what we're going to do is we're going to say 4 minus 3 is equal to C1 times 1 minus 1 plus C2 minus 2, 1. Plug those in, so you have 4 is equal to C1 minus 2C2 minus 3 is equal to minus C1 plus C2. I'm going to add these two together again. So what you're going to end up getting is you're going to get 1 is equal to minus C1, which implies that C1 is equal to minus 1. And when you plug that in, that implies that C2 is going to be equal to minus 2. Did I get that right? Minus 2 minus... I did that wrong. Just a moment. So that's going to be minus 1. Add those together. Minus 3 minus C2 is going to be equal to... C1 is going to be minus 1. Plug that in. That's 1 minus 4. Is that right? So, okay, I am... You will not get crazy decimals. And I am failing at solving this problem right now, which is a little bit embarrassing. What did I do wrong? Oh, that's what I did wrong. That's a C2, not a C1. That's why none of that worked out. Okay, so this is actually minus C2. So C2 is equal to minus 1. If C2 is equal to minus 1, then C1 is equal to 2. Okay, so then you're left with xy is equal to 2 times e to the minus t, 1 minus 1, minus e to the 3t minus 2, 1. Often it's you may be asked to combine them together if you want to write them as both x and y. So if I gave you the original equation as not a matrix, I might ask you to say what x of t is equal to. So then x of t is going to be equal to 2e to the minus t plus 2e to the 3t, and y of t is going to be equal to minus 2e to the minus t minus e to the 3t. Wait, why is there a 3? Oh yeah, that is a 3. Yep. Let's see. You won't get crazy decimals, right? No, you will not get crazy decimals because you will not need a calculator for this exam. So I can't give you any problems that would require you to use a calculator, basically. So you won't get crazy things like y of 1 is equal to 2. Or if you get a thing like that's... If I were to give you something like y of 1 is equal to 2, then I would let you leave your answer in terms of logarithms and exponentials. But the real answer is I will give you numbers that work out nicely. Or reasonably nicely, at least. Do we need to isolate for the x of y and y of y, or can we keep it as xy? That will depend on the problem. So if I gave you originally the problem as xy, as a matrix, then you can keep it as a matrix for your answer. But if I ask you to solve for x and y, then you should write it as x of t and y of t. Okay. I think that ends this portion of the review. So basically, this is all the ODE stuff. So these are your choose one of two problems on the final. So I've given you 4 different methods. You will have to use at least 2 of these methods. Well, you have to use exactly 2 of these methods to solve the 2 problems. You won't know exactly which 2 they are, but you'll have on each of them you'll have a choice. So I guess in theory that means that if you really, really studied 3 of these 4 methods, then you should be able to solve it, because then you would always be able to solve one of the 2 problems. You should study all of the methods because some of the questions might be slightly easier or harder, depending. Though I've tried to make them all about equally time-consuming, or for all 4 of the methods. So just keep that in mind. If you solve both but get one wrong, will I accept the correct one? So I will take, if you submit both parts of a choose one of 2. We will mark both of them and give you the higher of the 2 scores. So this is basically a slight advantage if you solve everything. So if you solve everything, then on the choose one of twos, you'll get the better of the two scores. I will not take the best 2 out of 4. So there will be one problem where you have a choice of 2. And then you'll have another problem where you have a choice of 2. And for on problem 3, for example, you'll have a choice of 2 different things. You will have to solve one of those 2 different things. So you can't just solve both of the parts on problem 3 and then be like, oh, well, I don't need to solve the parts in problem 2. So it should be very clearly marked. Basically, there will be one problem that is, where did I put that? So the way it'll work is detailed breakdown of questions. Let's go over into Chrome. So there will be 2 problems like this. On each of the problems, it will be the best out of 2. But you do need to solve one from each of those 2 problems. Does that make sense? Okay, great. Let's go back to finishing up the review since we're starting to run a little bit low on time. Okay, so power series, or sorry, not power series, phase lines. So you should expect to have to do a phase line problem. It will almost certainly be one about epidemics. So for a one variable autonomous ODE, x dot is equal to f of x, we can draw a phase line by just looking at the sign of x dot. The equilibria are the points where x dot is equal to 0. If x dot is greater than 0, then the arrows point rightward. If x dot is less than 0, then the arrows point leftward. If both arrows point inward towards an equilibrium, then the equilibrium is asymptotically stable. If both arrows point outward, then it is unstable. If one points inward and the other points outward, then it is semi-stable. So, for example, let me just do a couple quick ones. If I had the, so if when you graph out, so you don't have to, so opposing arrows are semi. So yeah, so let me go ahead and give you an example. So if we had x dot is equal to x squared, then the equilibrium for that is here at 0. And then is x dot positive or negative when you're greater than 0? Well, it's positive because it's always positive. It turns out that when you graph it, it actually looks something like this. You don't have to actually graph it, but sometimes that makes life easier. So we've graphed this, and both the arrows both point in the same direction. So they both so that means one points in towards the equilibrium, one points outward, and so then that makes this mathematically semi-stable. On the other hand, if you had, say, x dot is equal to x minus 1, x plus 1, so this is equal to x squared minus 1, well, what you're going to get 2 different zeros, or 2 different equilibria at minus 1 and 1. And if you look at these, if you do a sign analysis, you'll find that this arrow points to the right, this arrow points to the left, then this arrow points to the right. You just look to see whether x dot is positive or negative in that region. And so then that makes this asymptotically stable because both arrows point inward, and this is unstable since both arrows point outward. Why is the one on the left pointing to the right? For which one? For the... because here, x dot is equal to x squared. X squared is always positive unless it's equal to 0, right? If it's positive, everything points to the right. Positive, point to the right. Basically, if it's positive, things get bigger. And going to the right is getting bigger along the real line. Okay, so this is a phase line. You will have a word problem on this. If you've seen a very similar one on your problem set, you'll need to do a similar type of analysis. So how about the arrow in the middle? Oh, so what you need to do is you need to figure out the sign. So when you have, so what is x dot in this region here? So if you plug in a value for x dot in that region, say 0, you get x dot is equal to minus 1, so it's negative, and so it points points to the left. So what you need to do is you need to figure out the sign of x dot in each of these regions. if you could plot it out, which is hard, oftentimes it's easier to do a sign analysis than actually drawing the plot, but if you could plot it out, the parabola actually looks like this. It will be hard for you to, it may be hard for you to draw the graph flow, and so it's usually easier just to do direct sign analysis. So here x dot is greater than 0, here x dot is less than 0, and here x dot is greater than 0. And of course, at the equilibrium, they're equal to 0 by definition. Okay, so I won't actually be giving, I'm just going to review some of these other topics. I'm not actually going to work through examples, though I'm happy to do that in office hours if you need me to. But I'm just going to cover a couple more of the concepts, which we've been doing over the last several weeks, so hopefully it's a little bit more clear. So I guess this one is a little bit of review. So critical points of a multivariable function. Given f of xy, the critical points are where the partial derivatives f sub x and f sub y are equal to 0. The Hessian matrix is h of xy is equal to the second order derivatives, fxx, fxy, fyx, fyy. If the Hessian matrix at a critical point has all positive eigenvalues, then the critical point is the local minimum. If the Hessian matrix at a critical point has all negative eigenvalues, then the critical point is the local maximum. If it has opposite sign critical points, then it is a saddle point. Opposite sign eigenvalues. Eigenvalues. Okay? And similarly, if we have an autonomous 2D system, you'll consider the autonomous equation. The equilibria are when x dot and y dot are equal to 0. The Jacobian matrix is where the partial derivatives, f sub x, f sub y, and g sub x, g sub y, this is the Jacobian matrix, and its eigenvalues at the equilibrium, at an equilibrium determine its classification and stability. Positive real parts mean the trajectories go outward. Negative real parts mean that trajectories go inward. Opposite sign eigenvalues mean you have a saddle point. Non-zero imaginary components mean that the trajectories spiral. Furthermore, if you have a node if both eigenvalues are real and have the same sign. It's unstable if both are positive. It's asymptotically stable if both are negative. A saddle point is when both eigenvalues are real and have opposite signs, so one's positive, one's negative. A spiral is when you have a complex eigenpair. If the real parts are positive, then it's unstable. If the real parts are negative, then it's asymptotically stable. And a center is when you have a pure imaginary eigenpair, which we just call stable. And let me finish off with another, we're with a power series example, since that's the newest material that we've learned in this class. So the first thing is that we have this definition of a Maclaurin series. You can always use this to get a Maclaurin series of a function. This is by definition. F of x is equal to f of 0 plus f prime of 0 divided by 1 factorial x plus f double prime of 0 divided by 2 factorial times x squared plus f triple prime of 0 over 3 factorial x cubed, etc. So also, with power series, you can do standard manipulations like addition, subtraction, multiplication, and derivatives. Let's do some examples. So let's suppose I gave you the power series for sine of x. Sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, etc. If I gave you this power series, how do we get cosine? So what is cosine of x equal to? So one thing you could do is you could use this formula up here and directly compute it. So that will work. But another thing you can do is you could take a derivative. So if you took a derivative of sine of x, you get cosine x, right? So we know that this derivative is equal to cosine x. So what you can do then is you can just take the derivative of each of the terms of the power series. This is equal to 1 minus, well, what's the derivative of x cubed? It's 3x squared. But we're dividing it by 3 factorial, which is 1 times 2 times 3. So then the 3's cancel out. So this is actually equal to x squared over 2 factorial. And this is equal to x to the 4th over 4 factorial. Let me show this in a little bit more detail. So d dx of x to the 5 over 5 factorial is equal to 5x to the 4th over 1 times 2 times 3 times 4 times 5. The 5's cancel out, so this is equal to x to the 4th over 4 factorial, and so on. So if you know the power series for sine, then you can immediately get the power series for cosine by just taking derivatives. Other manipulations that are important are you can also substitute things in. So for example, if I wanted to get, what's the power series of cosine of, let's say, x squared? Well, if we plug this in, well, actually, let's do something slightly harder. Let's say I had x cosine of x squared. I want to know the power series of this. Well, then you can do this in multiple steps. You can substitute in x squared, and then you can multiply everything by x. So this would then be equal to 1 minus x to the 4th over 2 factorial plus x to the 8th over 8 factorial minus x to the 12th over 6 factorial plus x to the 16th over 8 factorial minus dot dot dot. But all of this is multiplied by x. So this is going to be equal to x minus x to the 5th over 5 factorial plus x to the 9th over 8 factorial. Oh, sorry, not 5 factorial. What am I doing? That's a 2. Over 2 factorial plus x to the 9th over 8 factorial. Not 8. I keep on... So, sorry about that. That's a 4. Let me fix these. Over 4 factorial. Oh, for x cosine x squared. What we're doing right now is we're plugging in... so the first step we're doing is we're doing list step. What's cosine of x squared? Well, you can just plug in x squared everywhere you see x in cosine of x. So that's x times 1 minus x to the 4th over 2 factorial, x to the 8th over 4 factorial, x to the 12th over 6 factorial, and so on. And now we're going to multiply everything by x. So you're going to get... Okay? So these more complicated manipulations include things like taking derivatives, or multiplying things together, or substituting in something. Does that make sense? Okay, so I think I mentioned last time, but I'll just go ahead and tell you that the power series that is on the exam is one that you may want to consider derivative. Do you always want to give 5 terms? No. So on the exam, I will be asking you for, I think it was a cubic approximation, in which case you need all the terms up to x to the 4th. So in this case, the cubic approximation of this is actually really easy, since it's just x. But I will be asking you for all the terms up to x to the 4th, basically. Because for any particular approximation, you only need terms up to some power of x. So the problem that is on the exam, you have a couple different ways of solving. One of the ways is you can use this formula. This formula will always work, though it might be a little bit time-consuming because you need to take quite a few derivatives. Another way is it will be something where you might be. I will give you a power series, and maybe you can manipulate it using some combination of these techniques. Okay, and I think like we are running a little bit over time. It's now office hours, so I will go ahead and end the review session here. This is all the structured review I had prepared. This covers basically all the problems on the exam to varying extents, and I have office hours. I will not stop recording, and we can switch to office hours. So if you have any questions, you can feel free to ask. Did you miss the part where you went over the Jacobian? Oh, this is actually really important. The exam starts at 8. It does not start at 8:10. So I will send out another announcement email. This is actually quite important. The exam does not start on U of T time. The exam actually starts at 8. I mean, if you arrive a little bit late, that unfortunately just means you won't have as much time. So, yeah. I will just say that if you can do the epidemic problem on the practice exam well, then you will be able to do the epidemic problem on the final exam. A cubic approximation is you write until you get to x cubed. So everything after x cubed you can cut off. So a linear approximation means you write everything until you get to x. A quadratic approximation means you write everything until you get to x squared. A cubic approximation means you write everything until you get to x to the cubed. A quartic approximation means you write everything until you get to x, including x to the fourth. A quintic approximation means everything including x to the fifth, and so on. I'm pretty sure I asked you for a cubic one. Did you miss the part where you went over the Jacobian? Let me switch back to it quickly. So the Jacobian matrix is just this matrix where you take the partial derivatives of respect to f and g. And then you plug in the values for at the equilibria. Yeah. Notice, and this is something I put these two together just to make a point. These seem quite similar. These Jacobians of a autonomous 2D system and Hessians of a single multivariable function. So I'll just leave you with that idea, since I did combine these two problems on the exam. Did you discuss Leslie matrices? Yes, I did. So I discussed Leslie matrices pretty early on. It'll be in the recording if you need it, but the basic idea is the first column, first column corresponds to all the arrows coming out of the first node. The second column corresponds to all the arrows coming out of the second node. The third column corresponds to all the arrows coming out of the last node. Yes, it turns out that there is a very deep relationship between the Jacobian of a 2D autonomous system and the Hessian of some particular multivariable function. The analyses even look very similar, right? When you're doing the analysis, you just look at the eigenvalues. There are other analyses, of course. There's things like the d-test. But if you use the eigenvalue analysis, that's actually quite similar between the two methods. I know you explained. Okay, yeah. So that seems. Let me actually. Okay, tell you what. Let me do something right now. Okay, let's go into here. So, let's type. Let's go ahead and put in my tag just so. Choice of problems, final exam. So, final exam template example. Let's see, what else did I do? I gave you a detailed breakdown of questions. So in the detailed breakdown of questions, we have problem 1. Problem 1, Leslie matrix. Solve this problem. Problem 2. ODE problem. You may choose one of the following two problems to solve. Y prime is equal to y, where y of 0 is equal to 5. 2. I don't know, let's say y double prime plus 2y prime plus 2y is equal to 4x. Find a general solution. Don't actually take these as problems. These are not problems that these are not, the problems on the actual exam are going to be significantly harder than the ones you just put on. So, problem 3, ODE problem. Choose one of the following two problems to solve. Let's say x dx plus x plus y dy is equal to 0, where y of 0 is equal to 0. I don't know if these are solvable. I'm just making stuff up right now. And solve the following system where x dot is equal to x plus y and y dot is equal to x minus y, and x of 0 is equal to 0, and y of 0 is equal to 1. Okay, does that answer your question? Then problem 4 is going to be a qualitative analysis. Solve both parts of the following problem. Solve all parts. So, problem 5. Oh, you guys can't. Yeah, let me scroll down a little bit. Problem 5, power series. Solve the following power series. Hint. I will give you a power series that may be helpful. Problem 6. What was problem 6? Epidemiology problem. Solve this with a phase line analysis. Okay. So this is the basic format of the exam. Obviously, don't assume these questions. These are not the questions that are going to be on your exam. But yeah, so the basic idea is I will write out these things. You'll choose one of two, and then on CrowdMark, there will be one place if you solved 2.1 and another place if you solved 2.2. And so then you upload it to the correct place. If you solve both of them, you can upload both of them, and I will give you the higher of the 2 marks for problem 2. And then for problem 3, the same thing. But you will need to solve at least one part from problem 1 and one part from problem, one part from problem 2 and one part from problem 3. If you solve all 4 of them, then you get your highest of the score for the 2 parts of problem 2 and the highest of your 2 scores for problem 3. Okay, hopefully this answers that. Let me go on to some of the other questions. So on the practice exam for problem 3, you got I is equal to 0 and 85. Could you please explain how you drew it on the phase line? Yeah, sure. Hopefully I did it right. Okay, so assuming I did all this math right, which it's possible I made some mistake, but hopefully someone would have caught it by now. So we drew out this 2-compartment model, right? And then what we did is we converted it into a one variable model. Just I dot is equal to this thing. So this is a one variable model because when you write things out, this turns out to just be one. You can rewrite s is equal to 100 minus I. And so you're left with I dot is equal to this thing, which it happens to be equal to. I made things a little bit complicated than I. But so you have this thing here. And we solved for lat is equal to 0, which gives you I is equal to 0 or 85, right? So if I is equal to 0 or 85, then that means the two equilibria are at 0 and 85. And then what you need to do is you need to plug in values to figure out whether I dot is negative or positive in each of these regions. So you have this I dot is equal to this formula, or this formula. Plug in values. When I is negative, it turns out that this will be negative, and this will be positive. When I is between 0 and 85, then I dot is going to be positive. When I dot is greater than 85, then it's going to be negative. So you need to check the signs in each of these regions. Does that answer your question, Ray? Let's see. When we solve the equilibria for nonlinear systems prior to the Jacobian, will the equilibria values be easy to solve, like as simple as the one on the practice exam? Which one did I give you on the practice exam? Will it be as simple? Let me quickly check. Where is my final exam? will be reasonable. So it depends obviously on what you're able to see, right? So like some people, the equilibria on the final exam are not hard. They will be easy numbers. I have made sure that they are easy numbers. Can you see them immediately? Some people could, like, I could probably see them immediately. I don't know if, like, is it as easy as this? I think it's pretty easy. I really do think it's pretty easy. So, yeah. It's hard for me to say that, but I do think it's pretty. It's relatively easy. Let's see. Oh, like you can see the equilibrium due to an easy system. It is an easy system. Like I made sure to make it an easy system. For the question you just did, wouldn't the 85 be pointing outward? So this is the equation, right? I minus 0.01 I squared minus 0.15 I. So if this is the equation, what happens when I is really, really big? When I is really, really big, this number is positive. This number, however, this I squared is positive, but it's a bigger number. So I squared is going to grow even faster, and that's a negative number. And so greater than 85 would point inward. So try it. Plug in 90 or plug in 100. 100 is probably easier. Plug in 100 into I dot and see what you get. When you plug in the number 100, you get, what would that be? 100 minus 100. You get minus 15. And so that points inward. Does that answer your question? Because you need to make sure that I have this I dot here, right? That's the equation that you care about. If you look from list step to list step, I multiplied everything by minus 1. Because once you set it equal to 0, you can just multiply everything by minus 1 to make it easier to solve. But you have to go back to what I dot is equal to. Yep, you have to be careful about that. This is why I said it's important that you figure out what I dot is equal to. You need to do it before you set it equal to 0. Because the moment you set it equal to 0, you might have multiplied by minus 1. Let's see, did I answer questions there? For the midpoint, we can test with 60 or 7. Yeah, so you can test with any point in that intervening region. I normally don't even test with an actual point. I normally do a sign analysis. But yes, you can just plug in any point in between the two. Practice exam problem 7 for the critical point 1, 1. Problem 7. For the critical point 1, 1, why is the number inside of the square root of the quadratic equation plus 5, which makes the eigenvalues real? Well, let's take a look at that. Sorry, there's a little bug here. Well, let's take a look at it. Why is it plus 5? Let me switch over to... Let me actually write this out, since it's hard to do on the fly. Okay, let's go over into OneNote. Okay, so we have this Jacobian matrix. You got the same Jacobian matrix, right? So we have the Jacobian matrix J of 1, 1 is equal to minus 2, 1, 1, minus 1. So how do we solve for the eigenvalues? So lambda plus 2 minus 1 minus 1 lambda plus 1 is equal to 0, right? So if that's the case, we have lambda plus 2 times lambda plus 1 minus 1 is equal to 0. So lambda squared plus 3 lambda plus 2 minus 1 is equal to 0. Hopefully this, maybe I might have made a mistake, which would be so let's see. So that's lambda squared plus 3 lambda plus 1 is equal to 0. So lambda is equal to -3 plus or minus the square root of b squared, 9. Oh no, I didn't make a mistake. So that's 9 minus 4ac, so that's minus 4 over 2. So that's equal to -3 plus or minus the square root of 5 over 2. Remember, lambda is equal, so if we have the equation ax squared plus bx plus c is equal to 0, x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. And it turns out that these are both negative because square root of 5 is less than 3. Yeah, you probably just made a mistake with your quadratic. Okay, I will leave this up for a moment for you to... Can you scroll up a bit? There. Yeah, and this is all still recorded, so you can look at this on the YouTube later as well. Let's see, did I miss any questions while I was doing that? Same Jacobian. Okay, so it solves that one. So always plug into the original. That was Ken's comment. It is safe to always plug into the original. If you know what manipulations you did, it can be safe to plug into a different version of it, but just you need to be careful about what manipulations you did. And I guess one other thing I should mention is, and I've mentioned this in one-on-ones with people, but I thought I'd put it in a recorded video, which is when you're doing, and this is actually generally true for any math homework or exams that you do, instead of just writing down it is a bad habit to just write down lots and lots of math. So I'm doing this now because I'm just explaining stuff, but if you were to do this on the exam, it would be helpful if you write down what you're doing. So you might be like, solve for eigenvalues. And then you might say something like the square root of 5 is less than 3, so one eigenvalue positive and other negative. So if you highlight the steps that you're doing, that makes it easier for us to give you partial credit if you get it wrong. So if you get it right, it doesn't matter because we'll figure out that you got it entirely right. But if you make mistakes in different places, we can give you partial credit if you make it clear that you know what you're doing. Then you just made an arithmetic error. So sometimes what happens is you have a big chain of math and you make some arithmetic error somewhere, but we're not sure what you've been doing because then all your numbers don't match the ones we have on the grading rubric. And if that happens, then all of a sudden it becomes a lot harder for me to figure out, or for your grader to figure out what you were doing, and so then we can't give you partial credit if we don't know what you're doing. So you will get partial credit if you make clear that you know what method you should have used, and then you use that method, but then you made a mistake somewhere. But we have to be able to tell that you were doing that. Is there any resource you would recommend for practicing Power and Taylor series? I can find one for you. I will put one on the website after class today. There are a lot of resources. Yeah, so I will look at a couple. Yeah, can we walk through problem 6 on the practice exam, please? Problem 6. Oh, yeah, so problem 6 on the practice exam. So there are a couple of different ways of doing this. One of them is you can do it directly using the Taylor series formula. So that just involves taking all these derivatives and plugging it into this equation. That takes time. That will work. It just involves taking lots of derivatives and evaluating at 0. Or taking 3 of them, in this case if it's a cubic approximation. The other way, the alternate method, is probably what you're asking about, right? So let me go over into the OneNote again, just so I can write stuff. So I told you e to the x is equal to the sum from I equals 0 to infinity of x to the I over I factorial. Let's write this out just to make it a little bit more clear. So this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And we probably don't care about the rest of the terms because we only care about cubics. But you might need to write them out depending on what I make you do. So then the next thing I do is I'm like, well, I want to know what e to the x squared plus x cubed is, right? So I'm just going to, let me actually write this up here, e to the x squared plus x cubed. So I'm going to start by saying, what is, oh, that's a highlighter. E to the x squared. What does that equal to? Well, here, notice that we have an x squared instead of an x. So everywhere you see an x, you need to put in an x squared. So this is equal to 1 plus x squared squared over 2 factorial plus x squared cubed over 3 factorial, etc. We can simplify that a little bit. So that's equal to 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial, and so on. So then e to the x squared plus x cubed, well, you just add x cubed to both sides. So that's 1 plus x squared plus x cubed plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial, and so on. But remember, we only care about the cubic approximation, so we can get rid of all that. And so therefore, we know that e to the x squared plus x cubed is equal to 1 plus x squared plus x cubed. So if I ask you for the word cubic, if I ask you for a cubic approximation, then it's not inclusive of the x to the 4th term. And let's see. Oh, Paul's online notes are usually pretty good. So here are some practice problems. Let me throw them in here as well. Yeah, I'll give you a hint. I'll give you the determinant. You don't really need it. I'm just basically giving that to you as a sanity check. If you write down a Leslie matrix and the determinant is not the one that, yeah, that's just me, Macy. That's just a sanity check. I will give it to you. You don't need to use it. Okay, and I also just threw up some practice problems. This is probably actually slightly more advanced than we're actually going to be doing, but hopefully that will be helpful. If an unknown power series happened to be the integral of a known power series, you could integrate the known power series, but then what would we do about c, since every time we integrate we have plus c? That is a really good question, and is a more sophisticated question than we're actually going to worry about. But the real answer is yes, you would have a plus c, but then you could solve for the plus c because the plus c is just the first term of the Taylor series, right? Yeah, so it would just be the very first term of the Taylor series, and then that's pretty easy because then you just need to take the Taylor series and take the first actually, you wouldn't even need the first derivative. That would just be the constant. So, yeah. Since the first term of the Taylor series is just f of 0. Yeah, so that's a slightly more sophisticated thing. I will probably not, I will not ask you to do, like, I won't say that it will be impossible to answer the question using that method, but it would certainly not be the most straightforward way of answering the question on the final do and use an integral. If you use an integration method to solve a power series like that, you do need to solve for C. So let me give an example, just because you're asking it anyway. So remember I said that cosine of x is equal to 1 minus x squared over 2 factorial. Actually, let's say, let me do it with sine. Let me make it a bit more clear. So sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, and so on, right? So now, we solved it a little bit earlier by taking derivatives, and when you take derivatives, you don't have a c. But now let's suppose that I decide to do it slightly differently. What if I am like, well, what is cosine of x equal to? Well, cosine of x, I know what that's equal to. That's equal to minus the integral of sine x dx, right? So that is a true statement. It's a little bit weird to do it that way, but you can do it that way. So what are we left with? So we're left with, let's see, so this is going to be minus x squared over 2, which is equal to 2 factorial, well, because that's that term. And what's this term? Well, that's equal to, we have a minus there, so that's plus x to the 4th over 3 factorial times 4. But 3 factorial times 4 is just 4 factorial. Minus, let's see, this term would be x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, etc., right? But because you're taking an integral, you also have to have a plus c. I'm going to put the c at the very front because the c is a constant term, and so it doesn't have any x's with it. So I'm going to put the c at the very front, and then you need to solve for the c, right? So you know that cosine x is equal to this thing. But how do we solve for the c? Well, we know that cosine of 0 is equal to 1, right? So we plug in 0 for x everywhere in this thing, then you're going to get that c is equal to 1, which implies that cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, dot, dot, dot. Will there be a question like this on the exam? Like I said, the question that I have designed on the exam does not require, does not need to be solved with an integration. Sometimes it might be possible to solve it with an integration if you do it cleverly. Like, for example, if I gave you sine of x and you need to solve for cosine x, you can do it 2 different ways. You could take an integral or you can take a derivative, and they'll both get you the right answer. Oftentimes, if you can take a derivative instead, that's easier, but I don't want to say that you can't use an integral. You might be able to. I haven't actually tried. But the important thing is that the question I have designed on the exam does not require you to take an integral. I'm mostly just answering this because Zainab asked a very good question, and I figured I'd explain it. Okay. Anything else? Okay, yep, good luck with studying, and I'll see you bright and early on Monday morning. Do either of you have any more questions, Ken or Ray? Yep, see you Monday. Good luck with the revisions. Any questions, Ken? If not, I'm going to stop recording and call it a day. Okay, I am going ahead and stopping the recording. I will see you on Monday, bright and early.